Okay, so let's get started here. So again, we're gonna do a little bit of an early review for the midterm that's coming up a week from Monday. And it's going to cover chapter 3 and chapter 4. And I would say you could expect the chapter 3 to be approximately 25 to 30% of the midterm, and then the chapter 4 might be like 70 to 75%. These are just like rough estimates of the topics. I have not written the test yet, so I can't say for sure how it's going to turn out, but hopefully that's a relatively good breakdown for you. In chapter 3, we just have 3 sections, 3.1 through 3.3, and then in chapter 4 we have 4.1 through 4.10, except 4.7. We're going to take that one off, and just be careful, I've got a recorder going there. Okay, so these are the sections and the percentages. So what I'm going to do is just very quickly give an overview of the material, and then I will mostly spend the next 2 hours doing practice problems that would be maybe similar to what I'm thinking about as being good test questions. And so then you guys can help me out with those. So in chapter 3, the main thing, of course, that is the chapter on determinants. And I would want you to be able to sort of have a good handle on the following things. I would want you to be able to calculate, I would want you to be able to compute the determinant of any matrix. Of course, we're talking only about square matrices. Let's say that they are n by n size. So you have to be looking at a square matrix, but I think that everybody should be able to calculate the determinant of any square matrix. Okay? It might be a huge matrix that doesn't have a lot of zeros in it, or it might just be a 2 by 2 or a 3 by 3. It could be anything. So we have 2 by 2 and 3 by 3 formulas. So if it's a small matrix, you can just use the basic formulas for a 2 by 2 determinant, right? So that would be AD minus BC, right? In the case of a 2 by 2. In the case of a 3 by 3, we might just resort to the arrow method. Okay, but those things you should definitely know. And then for larger matrices, you should be able to do cofactor expansion. So that's where you choose a row or a column and you find the cofactors on that row or column and multiply them by the entries from that row or column. And then you should be able to utilize EROs. This is where you have maybe a large matrix that does not have a lot of zeros in it, but by doing elementary row operations, you can introduce zeros into the matrix so that it's then easy to expand the determinant along that row or column, or you can make the matrix triangular. I'm just going to say to bring zeros into the matrix. You might go all the way to a triangular form, or you might not. You might say, I'm going to use EROs a little bit to sort of row reduce the matrix until I feel comfortable enough that there are enough zeros that I can then do cofactor expansion or something like that. So kind of a combination of those techniques there. So being able to compute a determinant using the formulas, cofactor expansion, and elementary row operations, this would be really excellent. In addition to that, you should know properties of determinants. So properties of determinants, so there would be a number of things here. How do determinants get affected by, EROs. Obviously that's going to be important if you're going to use EROs to bring zeros into the matrix. You need to know about the determinant of a transpose, of an inverse, inverses, products, things of that nature. So just know how determinants are affected by those kinds of operations. That'd be something that you would definitely want to know. And then so there's three main points. First one is be able to calculate a determinant. The second one is know the properties of determinants. And the third one is know what it's good for. What are the applications of determinants? So applications of determinants, this would include, test for invertibility, right? So this is how we can test if a matrix is invertible. Okay, so remember that for an invertible matrix, the determinant is not 0, right? So the determinant of A is not 0 for an invertible matrix. Moreover, we can actually come up with the inverse of A using a determinant-based approach, which is the adjoint procedure. So A inverse is, remember, 1 over the determinant of A, which is a number, multiplied by the adjoint of A. So you'll want to know that. And this is where the adjoint of A, I'll just remind you here, it's the matrix of cofactors transposed. So we have to transpose the matrix of cofactors. And if we have that, then we can use this formula right here. Pretty easy to use. This is particularly handy for larger matrices where maybe I ask for a specific entry from that matrix. I'm going to do an example of that in just a minute to show you where this would be useful. We of course, in Chapter 2, we learned the Gauss-Jordan method for finding the inverse of a matrix. But the thing with that was that can be pretty tedious, and doing the elementary row operations, especially when fractions are involved, becomes quite hard to keep track of by hand. Whereas the nice thing about this formula for A inverse is that sort of the fraction is kind of factored out in front of the matrix. And then the adjoint is something that, assuming that A has whole numbers in it, the adjoint will have whole numbers in it. So you're not dealing with fractions quite so severely when you use this approach here. Okay, then there was Kramer's rule. And that was for solving an entire linear system, right? So if we had AX equals B, right? And again, this is for an invertible matrix A. So if A was invertible, we can actually solve this system without ever actually finding A inverse. We can simply write the ith entry of the unknown vector x. If you remember, we can write it as a fraction. The determinant of A on the bottom. And then on the top, we had the determinant of B sub I. That was the matrix, if you remember from Chapter 3, where you take the matrix A and you replace the ith column of A with this right-hand side vector B. Okay, so if you do that, then you get the formula for a particular unknown in your linear system. Okay, and then finally, the last application of determinants that I think is worth knowing, which actually has a lot of importance in Chapter 4, is the physical interpretation of the number that you get. So especially in the 2x2 or 3x3 cases, we talked about the geometric interpretation. Remember that if you look at the rows of the matrix or the columns of the matrix, you can view those as vectors. The rows of a matrix, and so if I have just a 2x2 matrix, for example, right? The rows of that matrix form vectors in R2, which we could visualize somehow. And the point is that those vectors form a parallelogram. And the area of that parallelogram is what is measured by this determinant of A. If it's a 3 by 3 matrix, for a 3 by 3 matrix, instead of area, you're going to be getting volume. But the cool thing about it is that if you get 0 for the determinant of your matrix, that's a way of being able to tell that your vectors are all, well, it's a way of telling that your vectors are linearly dependent. Like they're all lying in the same plane, or they're all on a single line or something like that, right? So there's a connection here between determinants and linear dependence and independence, which is something that comes up in chapter 4. Okay, so this right here, at least 25-30% of the midterm is kind of these 3 main bullet points. How do you find determinants? What are their properties? And what do we use the determinant to do for us? Okay, any questions so far on that? This is just a quick little overview on chapter 3. If not, then what I think I might do next is do a few examples that are based on chapter 3. Before I go to chapter 4, let me just do some chapter 3 examples. And some of these will be theoretical and some of them a little more computational. So let's try this example. And I'm going to type up these problems, by the way, and post them on that yellow screen. I just haven't done all of this stuff yet. But anyway, if we let the matrix A be as follows: 2, 0, -1, 3, 0, 1, 0, -1, 0, -2, 1, 1, and 3, 1, 0, 0. If we take that matrix, let's find the 4, 3 entry of A inverse. So there are 16 entries in this matrix. We're not being asked to find all of them. I mean, one thing you could do, of course, is the Gauss-Jordan method. You could take this matrix, augment a 4 by 4 identity matrix here, and then just row reduce the left side to the identity matrix. The inverse of your matrix would be on the other side, right? Okay, we could just do that, but the thing is that that's going to be tedious. It's going to have fractions, and it's going to be easy to make a mistake. We should take advantage here, guys, of the fact that they're only asking us for one particular entry of the matrix. So when we're looking at A inverse, we only have to figure out one particular number. And so that's the sort of, to me, the tip-off that we should think about the adjoint method. Does that make sense? We're going to use the adjoint method to do this. So let me just recall, I already had it up there a moment ago, but I'll write it down again, that the formula for A inverse is 1 over the determinant of A times the adjoint of A. Okay, so this is the adjoint method for A inverse. So the thing is, if we want to calculate a particular entry, if I want the 4, 3 entry here, right, then I can kind of look at the other side of the equation. What would it consist of? Well, it's going to have a determinant of A on the bottom, right? And then the 4, 3 entry of the adjoint. What would be the 4, 3 entry of the adjoint?
3, 4 of mine. 3, 4.
The 3, 4 cofactor, exactly, because remember, the adjoint is the transpose of the matrix of cofactors. So when you transpose the entries of a matrix, the subscripts get swapped. So the 4, 3 entry comes from the 3, 4 cofactor. Okay, so we really just have to calculate 2 things. We have to calculate the determinant of this matrix, and we have to calculate the 3, 4 cofactor. Is everybody with me so far? Everybody good? Okay, great. So which one do you want to do first? I don't care.
Determinant.
The determinant. Okay, let's do the determinant of A first. So the determinant of A, any suggestions for how to evaluate this determinant?
Cofactor on row 2.
Okay, I can look at I could decide that I'm not happy with any row or column of this matrix, and I just want to do some elementary row operations first. You could do that, but if you're okay with it as it is, there are some zeros in it. We could choose a row or a column to expand along. And when you're writing this up, especially on an exam or whatever, it'd be great if you could tell me like which row or column you're using so I can make sure I follow your work. So which row or column do you guys recommend we use here?
Row 2.
Row 2? Okay, so we could use, there's lots of choices actually, but I would choose a row or a column that has a lot of zeros in it. So the second row would be good. So I'm just going to say right here, expand row 2 to remind myself of that, okay? Now, the other thing you need to remember about the cofactors is that they alternate signs. So we have this plus minus pattern that's kind of like this. Okay, so along the second row, notice that the first entry has to be minus. So it's actually negative of 0. Okay, and then plus 1 times the determinant of a matrix I'll write down in a second. And then minus 0 again, and then plus negative 1 times another determinant of another matrix that I'll write down in a second. Okay, so this is going to give me the determinant of, so what I have to do, remember how I do this? I cross off the row or the column that I am centered on. So I'm looking at this position, I cross off that row and column, and I write down the rest of the numbers that I see in the matrix. 2, -1, 3, 0, 1, 1, and 3, 0, 0. Okay? And then minus the determinant of the matrix that I get when I cross off the, you have to be a little careful. I would recommend using a pencil so that you can uncross things as you go along. So the 2, 4 position is over here. Right, and we've already taken care of the -1, so I just have to write down a 3 by 3 matrix there too. So 2, 0, -1, 0, -2, 1, and 3, 1, 0. Okay, great. And now can somebody just tell me at a glance what this determinant would be? See, here's the thing. You can use the arrow method. Yeah, right. You can use the arrow method, but you don't need to because the bottom row is so easy to expand. Just do expansion on that bottom row. What'll happen is you'll get 3 times this little 2 by 2 determinant, and that'll be it. Because there's no more terms here. There's a 0 here and a 0 here. So it's just going to be 3 times this little 2 by 2 determinant, which is -4. So 3 times -4, and then minus, and then I come over here and I have to do this determinant. This one isn't quite so nice because although I have some zeros, they're not in the same row with each other. So maybe I just get lazy and just use the arrow method, recopy the first 2 columns and do my diagonals. So I'm going to get 0 plus 0 plus 0 for the first 3 diagonals, and then minus 6 minus 2 minus 0. So use brackets and be cautious about sign errors. That's generally what is the most common mistake here. But we get -12 minus -8, which is -4. Okay, so the determinant is -4. By the way, that tells me, for example, that the rows of this matrix are linearly independent. And so are the columns, right? If you were to row reduce this matrix, you would get a pivot in every single column right down the main diagonal, right? So, yeah, just to tie it in with some of the chapter 4 ideas. If I had given you the vector 2, 0, 0, 3, 0, 1, -2, 1, -1, 0, 1, 0, and 3, -1, 1, 0, and I asked you, are they linearly independent or linearly dependent in R4, you would now know that they are linearly independent because you got a determinant that's not 0. So that's just a nice tie-in with the next chapter. Okay, Let's do the 3-4 cofactor, because we have to figure that out to finish this calculation here. So for the 3-4 cofactor, remember that because 3-4 is an odd position right here, there's a sign change. I'm going to just put it down right away. The sign change, and then I'm going to take the determinant of the matrix that I get when I cross off. So row 3 and column 4. Be real careful here. After I cross off row 3 and column 4, I have 2, 0, negative 1, 0, 1, 0, and 3, 1, 0. Did I do that right? I think so. Okay. So what is, so we have negative of this determinant. What is this determinant going to equal? Pardon? Positive 4. That's not what I'm getting.
Negative 3.
Yeah, I think it's, if you expand the middle row, for example, you just have 1 times 2 times 0 minus 3 times negative 1 is 3. So you just get negative 3, right? Great. So minus of 3 divided by negative 4. So my answer for the 4-3 entry is negative 3 divided by negative 4. Or in other words, 3/4. So that's the final answer, 3/4. Okay, does this make sense? Now I could also give you a linear system. And I like to do part A and part B a lot of times. I could give you a linear system where I do something like this. 2x minus z plus 3w equals 5. And then, I don't know, y minus w equals 2. And negative 2y plus z, was this a 1? Yeah. Plus w equals 0. And then 3x plus y equals 4. I could follow up with a follow-up question where I give you a linear system like this, and then I could say something like solve for z. I could say specifically to solve for one of the variables. In this case, there are 4 unknowns, and because this matrix, the coefficient matrix for this system is just this one, we already know that it's invertible. Right? Remember that if the determinant is not 0, then your matrix was invertible. So since this is an invertible matrix that I'm dealing with, there is one unique solution to this system. There has to be exactly one. And I'm not asking you for the whole solution. I'm just saying, tell me what z is. So what would you use to solve that problem?
Kramer rule.
Exactly. You would just use the Kramer's rule, and you would just simply say that z is equal to, what is it? The determinant of a goes on the bottom, which we already know. And then on top, we would put the determinant of what I would call b3. That would be the third variable is the z variable. So you would take this matrix and replace the third column with 5, 2, 0, 4. And then you'd have to calculate another determinant again, right, by doing another cofactor expansion or something. Maybe I'll skip doing that because it's just more of the same kind of calculation, but does that make sense? A lot of times what I think is hard for people is not actually executing the steps. It's more deciding what tools. You have all these tools, right? It's like, how am I supposed to approach a problem? So on this one, for example, solving this linear system, you're thinking, well, wait a minute, I learned that in chapter 2. Solving linear systems was chapter 2. Why is he asking about that now? This is chapter 3 and 4 for this midterm. Well, the reason is that you're not supposed to use the chapter 2 approach. You have to think, okay, so what have I learned in chapter 3 or later that would actually be relevant to this? And the answer is Kramer's rule. Okay. So being able to pick off when you're going to use which of the tools that you've learned is a really important thing to be able to do. Okay, I'm going to give you guys another couple of problems here about determinants, as long as we're practicing. So let's do another example. Okay, so let's do this one. Let's assume that A and B are 4 by 4 matrices with the determinant of A equal to 2 and the determinant of B equal to 3. Here's what I want to do. Can we try this one? Let's find the determinant of A inverse B transpose times 2B quantity inverse. Try this one real quick. So this one is not a specific matrix. This is a problem where I'm probing you about properties, right? Properties of determinants. Anybody have any suggestions here how to separate it? Okay, so we can write it as the determinant of what? How would you break it up? And try not to do too many steps at one time. Let's kind of do it slowly.
B transpose?
Well, I can write down B transpose like that, you mean? Okay, so what's that equal to?
1/3.
Okay, when you transpose a matrix, what happens to the determinant? Let's say you get on the test and you have a blank and you blank out and you don't remember. You know what you should do? You say, oh, I don't remember what happens when I transpose it. So then you go back to something familiar and you say, well, if this was ABCD, the determinant would be AD minus BC. If I transpose that, if I switch the B and the C, I get AD minus BC again, right? Oh, it doesn't affect the determinant at all. So if you forget something, maybe an example can trigger for you what you were supposed to say. So the determinant of B transpose is the same as the determinant of B, which was given as 3. Okay, so that's good. What else? What else can you tell me? Okay, we can look at A inverse. What is the determinant of A inverse in this case? Okay, so that one is reciprocal, right? So we take the reciprocal of the determinant of A, which would give me 1/2. Okay, what else do I need to look at?
The determinant of 2B.
Okay, the determinant of 2B. I like the way you guys are breaking this down step by step for me. What would be the determinant of 2B?
2 to the 4.
2 to the 4 times determinant of B.
Right, so don't forget to power up the coefficient here. So the scalar 2 right here is scalar multiplying each row of the matrix B. So there's 4 rows. This 4 by 4 is actually important for doing the problem. So I get 2 times 2 times 2 times 2 times 3. And so this would end up being 48. Okay, and so then I guess this is 2, you have to be careful here. This is 2B quantity inverse, not 2 times B inverse. So now I have to find the determinant of 2B quantity inverse, which again is just going to come from taking a reciprocal here. Okay, so that's all the information that you need. And now how do we put it together?
We also need
Don't we need to know what the A inverse transpose
It
is?
doesn't affect
A inverse transpose. Well, it depends on how you're breaking this down, actually. Like, are you trying to actually simplify this here? So this one, as you probably remember from chapter 2, when you have a transpose of a product,
Oh, yeah. That's true.
you reverse the order of the transposes. This is fine. You can do this. So you need to know the determinant of B transpose, which we do. A inverse transpose, what would that be?
Just 1/2.
It's still 1/2, right? You're just transposing the matrix A inverse, so the determinant doesn't change. And then 2B inverse is 1/48. What do I do with all the individual inverses, or all the individual determinants? Multiply them, exactly. So the determinant of the whole thing, A inverse B quantity transpose times 2B inverse, therefore is just going to be 3 times 1/2 times 1/48, right? And that can be simplified to 1/32. That look okay? Okay, let's try a slightly harder one. So this is just refreshing our memory about properties of determinants. Let's do a slightly harder one unless there's any questions here. Everybody's okay for now? Okay, let's try another example. Let's do this one. Suppose A and B are n by n invertible matrices. And assume that AB is equal to negative BA. Let's show that n is even. Kind of weird. Has to be a 2x2 or 4x4 or 6x6 or 8x8, right? You can't have odd-sized matrices. And I've asked this question before on exams that I've given, and usually what people start doing is they start writing down 2x2 matrices, you know, and playing with it like this, but the trouble is that you don't know that n is actually equal to 2. N could be some other number, and the whole point of this problem is actually to show that the n must be even. So some of you who've had a little bit of theory of proof, you might think, well, I could just assume that n is odd and try to find a counterexample. You know, but if n is odd, then there's still a whole bunch of choices. N could be 3 or 5 or 7 or 9. This is not clear how to really work with that. So if n was odd, you could try a 3x3 matrix, but again, this is just going to be a mess, you know, trying to write out, you know, something like this, and it's only going to convince me that you don't have a 3x3 option. So this is one of those problems where you are much better off sticking to a very high level view of the matrices. By that I mean very abstract view. Don't go down that rabbit hole of trying to like get the entries of the matrix written down and start multiplying a bunch of stuff out. It just becomes a disaster, right? This one should be done very surface level. And as such, it's going to be a very clean solution. We will not need any more room than you have right here. So I think I asked this on a test one time, and like nobody got it right. So I said, all right, the next semester I'm going to ask it on a test again, but I'm going to give a hint. And so the hint did make a big difference. It did help. You guys really don't need this hint because we're already talking about it, but the hint here is to use determinants. It may not seem obvious without that hint that that's the best way to approach this problem, but in fact it is. So let's try and use determinants. Now there's no determinants mentioned in the problem at all. It's never mentioned. So are there any, does anybody see any way to sort of bring determinants into the picture here?
I take the determinant of both sides of both A and B.
This one?
Yeah.
Okay, so guys, this box equation here, this is two matrices equal to each other. If two matrices are the same, then their determinants have to be the same, right? So that's exactly what I would also recommend that we do. So taking determinants, right, we're going to get that the determinant of AB is equal to the determinant of negative BA. Okay, so we just simply start off with the original equation, And if we just take the determinant of both sides of it, this is what we have. Okay, what would be your next step, do you think?
Use. You can break them up as problems.
Break them apart, right? Yeah, exactly. I'm just going to break them apart. So the left side would be the determinant of A times the determinant of B, and the right side would be determinant of negative B times the determinant of A, right? Yeah, so something like that. That look okay? Okay, why can I divide by the determinant of A?
Determinant.
Why is it not 0?
Because it's invertible.
Aha! There's always a reason for every assumption, right? The fact that your matrices are invertible means that the determinant is not 0. So since A is invertible, the other weird thing is I don't really have n anywhere in this equation, so you guys are going to have to think about where the n is going to come into it. But since A is invertible, the determinant of A is not 0, and so canceling, so we can cancel it because of that. By the way, these are just numbers, so the fact that one of them's on the left side here and on the right side here makes no difference. So we just cancel and we get determinant of B equals determinant of negative B. Okay. Now what can I do with from there?
You have a scalar of -1, and it would only equal determinant of B if n is even.
Okay. So I have a scalar of -1, so what can I do here?
Take it out to negative 1 raised to the n.
That's right. -1 to the n times the determinant of B. It's just like any other scalar. You can pull it out. And now, again, since B is invertible, we can cancel that as well, right? So canceling the determinant. So this didn't go too badly. Canceling the determinant of B, which is not 0 for the same reasons that A was invertible. B is also invertible, so we can cancel the determinant of B. We get -1 to the n is equal to 1, and thus n is even. That's the idea. That's the idea. Okay? So just another example of a problem where you're using determinants to, properties of determinants to solve a more theoretical exercise. I will be asking you to do some proofs. Not a massive number of them on the test, but there will be some that are kind of the nature of these last couple of examples. So it'll be a mix of the regular computational stuff together with a little bit of the proof-oriented stuff as well. And I just wanted to give you an idea of maybe a couple of examples of the types of problems that I could ask. So, any questions here? Okay, if not, I was going to recommend that you would probably be wise to go back to the old group works that we had since the first exam. There's some nice group works we did on determinants. I think group work 5 and 6 maybe. There's a couple of them. And I would recommend looking at those again to kind of get yourself brushed up on that. Okay, so that's a good overview of determinants. We need to know how to calculate them. We need to know their properties. And we need to know the applications of determinants. And some of those applications come actually in chapter 4. So with that, I'm going to call it good for chapter 3. I'm going to turn off my video, and then we'll move on to chapter 4.